right, welcome back everyone. We have our simple ray tracing algorithm now, and we also have our simple shading model that we can use. And for the rest of today, we want to talk about more advanced shading methods. And one important thing that we talked about already last time for projective methods is different methods to produce shadows. And in ray tracing, this actually works relatively easy because in ray tracing we can use so-called shadow rays or shadow feelers, and the idea is that we take a ray. If we have a point and we want to know if this point is in a shadow or not, we just shoot a ray towards the light, and if that ray intersects with an object like you see it here on the right side of the image, then of course we know there is no direct connection to the light, so it must be shadow. And if we shoot it towards the light and we hit the light source, then of course we know there is no object blocking the light, so we are not in the shadow. So this is of course very simple, and the key here is of course that we have already, if we have implemented our simple ray tracing algorithm, then we have this already in place. We just need to do the extra calculations, but the procedure is the very same that we use when we shoot a ray from the eye towards an object, towards the screen, or through the pixel on the screen towards an object, and then do an intersection test. It is the very same thing, so we can just use the same thing that we already implemented also to have the shadow feelers. There is only one thing when we implement it where we have to be careful. That is that we can have precision problems when we are very close to the object where we start our ray, which is why in practice we usually don't start at the point itself, but we introduce a small epsilon value, and then we don't start from, like we do it when we do the normal ray tracing from the eye. We start with this epsilon and not from 0 here, because when we and we don't have this problem of course with the regular ray tracing, because then we only look for t larger than 1, because we only shoot the ray behind the screen, whereas here we're shooting it from 0. So if we do the ray equation in a way that we start from there, then we add a little epsilon, which means we're just shooting it a little further away from the point, but that should give the same result unless the other object is extremely directly in front of it, of course. Good. Yeah. Another thing which we actually already had also in a context of the previous shading model in relation to Phong shading is mirror reflection, perfect reflection. In Phong shading we had it in relation to figuring out where is the best, the brightest, the angle where you have the brightest light when you have these shiny spots, for example, on a marble. Here we want to use it to create a mirror. And the idea is of course the same, or the principle is the same. We say if we look at the spot and then we get, if we want to have a perfect mirror, we see at this position exactly what we would see if we have a reflection at exactly the same angle. So if there is, I don't know, some object here, then this object appears also here when we look at it from this direction. And this is the same that we used also for the Phong shading, where we used an almost similar equation here. I'm saying almost because there is a slight difference here, because for the Phong shading we had also the reflection vector, the normal vector, but we had the eye vector pointing in that direction. Here we're shooting the ray from the eye, which means this vector has a different direction. And if you remember, for the Phong shading, we showed that this is indeed this equation that leads to it by saying if we want to go from here to, if we want to represent this reflection vector, we take the vector d, but in the Phong shading it was L and then minus L. In this case it is of course the vector d, because it already points in that direction. We just have to let it start here, and then we go up here in the direction of a normal, but with a value lambda times n, and then of course 2 times this, and this is where this 2 comes from, and where the n comes from, and where the d comes from. Only this lambda we have to specify, and that we can do with the cosine here. And because n and d are all normalized vectors, we can get the cosine of the, no, we can get the cosine of the angle times the length of the vectors is the scalar product, but the length of the vectors is 1, which is why it's just the cosine is just the scalar product, which is why we can get here, we don't have to calculate the cosine, but we just put the scalar product here. The only difference is here this minus. That is a little difficult to see, because if you look at the image, you would assume it is plus d plus n, so it should be a plus here. But again, if you don't if you think this is a mistake, you can just use a simple example. Just fill in 2 points, take 1, 0, and here a normalized vector in that direction, and calculate, and you will see it works out. And the point is, of course, when we do the scalar product between n and d with this angle here, we have to be careful that d is pointing in this direction. Now here we had the scalar product of the angle phi pointing in this direction, of the vector pointing in this direction. Here d points in the other direction, which is why the scalar product will lead to this minus value here. Good, but other than that, it is quite the same, only now we have it with this ray tracing. Of course, we can very easily make this also recursively, but especially with perfect reflection, we have to be careful that we make also, it can happen, for example, that if you're in a closed room, that you have constant reflections, and then you come in a circle and the reflection just bounces from one point to another. So you have to add a certain maximum recursion step to it. There was a question. No, I'm just very often confusing Greek letters. Yeah. It's not another angle, it's just theta. Sorry. Yeah. Good. Yeah, it's late in the day for me too. All right, another advanced shading method we want to look into is so-called refraction. Refraction is, so you see all these advanced shading methods that we have in ray tracing, or we have a lot of like advanced shading methods, special effects in ray tracing that can be very easily done with following light and following rays, because it integrates so nicely in our approach. And refraction is one of them. Refraction is the characteristic that light has when it travels through a transparent medium. So for example, if you have a glass like in this image here, and then the light falls through it, the light doesn't usually go directly through it, but it is kind of refracted, kind of shifted, tilted. And this is something that you can also quite nicely calculate and simulate with ray tracing. But for that, of course, we need to know the physics behind it, what happens when how this is really the characteristics of it. And this is modeled by the so-called Snell's law, which says that the refraction vectors, or the angles of the vectors of the light, depend in this from each other with this relation between the two angles, or the sine of the two angles, and these two so-called refraction indices n and nt, which are just indices or values specifying the refraction level that you have in a material. So for example, if light travels through air, then of course there is no refraction, but then if it hits on a glass, it is refracted in a certain way. If it hits on a different material or a different type of glass, it is also refracted, but at a different angle or a different style. And this is modeled by this refraction index. So we have here the refraction index n, and then we have here the refraction index nt, and for these angles and these refraction indices we have this relationship. Again, of course, when we go outside, then if this is the same material as when we had when we entered, then we have again this refraction index n here. Of course, now this nt comes from n target because it's a target media. Here, of course, it switches. It goes from the target to the original one, which is also why the angles are just reversed. So we have here phi and theta. This time I got it right. And so you see there is symmetry because the same relation, of course, also holds here. Only then t and the angles are different, but the equation is symmetric. So this is how it evolves physically, and now of course we want to know how can we use this to calculate this target vector t, the vector inside the refracted vector inside of our medium. And to do this, first of all, I hope you immediately understand why it says here that we have a relation with sines. It would be more convenient to have a relation with cosines, because of course, because of the scalar product, we can easily calculate the cosine. So but we also have this so-called one of the trigonometric these so-called trigonometric identities, which is just a characteristic of these trigonometric functions, which says that the sine to the power of 2 of an angle plus the cosine to the power of 2 of that angle equals 1. And if we combine this, or if we use this in Snell's law, we can express Snell's law also with cosines instead of sines. Now this is it looks complicated, but it is actually very simple. If we take Snell's law and a trigonometric function, and we want to get rid of the sine, so we bring the sine here to one side, and then we see here we have the sine to the power of 2, so we make this the same here. We bring these ends together and we bring the angles on one side, so we have the sine here. Then we make the sine to the power of 2, and then we put here for alpha we set phi in, which removes the sine on the left side. Then we set for alpha we set theta, that removes the angle on the right side, and then we have exactly what we had here. So by the way, for the exam, if you need something like that to solve a question, then we would of course give it to you. So like I said last time, in the midterm exam you should know the simple things, or the straightforward things like the sine and cosine, how the function looks, how the trigonometric relations are. But if there is a more complex thing, then we usually give it to you, and then as a hint how you can solve it. Good, so we have the cosines now, and we want to use that, but we still want to have this refraction vector. And now we know how to calculate the angles, and we need this refraction vector. And to do that, we assume that the direction vector, the incoming vector and the normal vector are normalized, so have the length of 1. You will see later why this comes in quite handy, as very often in graphics, of course. And then we say, first of all, the vector t is in a plane that is spanned by these vectors d and n. And then we describe this vector in a way, in an orthonormal basis, by choosing a vector b which is on the surface and in that plane that is defined by d and n. Because if we do that, then we can express the vector t as a linear combination of these two vectors, because then the vector b and the vector minus n represent an orthonormal basis, and then we can describe the vector t like that. And because we have them all normalized, we can also see that these xt and yt, that is looks a little confusing. That should be minus n and not yt minus n. It's yt times minus vector n. Then we see that the xt and the yt are just the sine and the cosine of that angle phi, and then we can describe t as depending on b and these two trigonometric functions. In the same way, we can describe the vector t now d. Now, of course, we already have the vector d, but we want to do that. We want to solve for the b. Then we can put it into t, and then we can describe the vector t in this way here. Now, of course, you can say we already have it here described, why this at the bottom looks much more complicated. But you see here at the bottom we don't have any trigonometric functions here. We just have normal arithmetics, but no trigonometry and no angles in there, so we can describe this vector t without any angle and any trigonometric function. And another interesting observation we have here a square root, which of course can get negative, But the negative case is then exactly the case when the relation between n and nt is in a way that there actually is no refraction at all. And this is called total internal refraction, which means that there is no light going through the material. Good. Are there any questions? No? So next time we'll talk about more advanced ray tracing algorithms, also more ways to speed up ray tracing, because like I said, ray tracing is a very slow approach, so we'll talk about approaches to speed it up. Here are a little overview, because things will be a little bit different next week. First of all, the tutorials. Forgot to write it down. Of course, the solution for the 5th tutorial will go online tonight. For the 6th tutorial, I will only put the first part online, because this is the last tutorial. That means it also covers the lecture next week, and I do not want to make the tutorial before I prepare the lecture, because if I make changes in the lecture later, you might end up with the wrong tutorial. So that's why the second part of the tutorial will go online later, but I will put the first part online already, because some people might want to already look into it. The next tutorial session with TA is then of course on Tuesday, and also there is a tutorial on Thursday, which will then be the last tutorial. So you can also come, of course, to the tutorial and ask questions about all the other stuff there. The other thing that will change is that there will be special practical sessions next week, because there is of course the deadline on Thursday for the 3rd practical, which is why we have, again, the teaching assistants were very nice to you, and they volunteered for to make extra hours. In particular, also Alexander said that last time he realized a lot of people were leaving at 1 o'clock to the data structure lecture, so the extension of 2 hours was kind of not very helpful for you, which is why he volunteered to only make it to 1, but then come back at 3 o'clock. So if after the lecture you want to go there again, he will be there from 3 to 5. Tuesday we already have the session. Wednesday will be an extra session again. Alexander will be there from 11 to 3. And on Thursday is the regular session again. And today only one teaching assistant was there, because the other couldn't make it, but then again 2 will be there. Good, and then it's the deadline, and then the following week is the exam. And the only other thing that is here now is, you see on Tuesday there is a lecture, but there will be no lecture on Thursday. Originally I announced the lecture, but only saying summary and conclusion, and I usually do this to have a little buffer in case anything goes wrong here or so. Then I still have one date where I can finish up everything, but I'm pretty sure I can finish up everything on Tuesday, so there will be no lecture on Thursday. But there is also no reason to get sad about that, because there will be another event at the very same time, also here in this room, which is Bas and Maries, I think, already mentioned it when they had their introduction for the 3rd practical, that they might give a talk on advanced graphics models and advanced graphics techniques, and that's exactly what they are going to do next Thursday. They will do it at this place here, at this, also at the same time spot, so directly after the deadline for the practicals. So if you're done with the practicals and want to see what's next, then you can go there. Of course, this is not official part of the course. This will officially be announced to all students, so you are free to go there. But if you liked the course, then I think you will I'm very sure you will also like the talk. If you didn't like the course, but if you like graphics, then you will probably also enjoy it. If you liked neither of them, then you probably better stay home and learn for the exam to make sure that you don't have to do it again next year. Good, so here is some detailed information about it, but I will also post this on the website. Good. Any questions? No? Then I see you again on Tuesday.